this video, we're going to put into practice everything we've learned about maximization and minimization. So we learn about the first and second derivative tests and related techniques in order to solve applied problems, in order to put them into practice. So in this section, we're going to talk about the general approach you would take to using those techniques in the context of a real problem. And then we're going to look at some applications where maximization and minimization may be helpful. So in many real-world applications, we want to maximize or minimize some quantity that is specifically subject to constraints. The idea is that in real life, of course, we have finite resources. We're limited based on scarcity. We can't just make and make and make and go and go and go. There are limitations on what we can do, what we can use. And so maximization, minimization is going to be important, taking into account the limitations that we have on our resources. So we're going to use techniques that we've discussed already for finding our absolute maximum and minimum values, and we're going to take this information in these techniques and we're going to combine with additional information regarding the specific limitations on our resources in whatever situation we're looking at. So in the kind of problems we're going to work on in this section, we have two goals in mind. The first goal is to find the maximum or minimum value of whatever quantity has been identified. Now, this may just be an abstract value, or it could be something specific to a particular situation. So something like cost, or maybe something like area if we're talking about a geometric type problem. We're going to focus on either maximizing a value or minimizing a value, just depending on the situation we're looking at. Now, in addition to that, the idea is we're taking one big quantity, either maximizing it or minimizing it, but the idea is that we also have resources that are thereby contributing to whatever quantity we're looking at. So we're focused on how those resources are limited, using those limited resources in the most effective way to either maximize or minimize. So we also want to determine the values of the inputs, or we can think of them as components, that lead to the maximum or minimum value for our quantity. In other words, if these particular inputs contribute to this quantity, which we can think of maybe as a total, what are the values going to be that contribute to either the maximum or the minimum value of the quantity of interest? So we're going to do a couple of examples that are a little bit more abstract, just to look at the general technique for solving these kinds of problems. And then we'll also look at a few application problems where we actually are going to put these techniques into context. So our first example, we want to maximize Q. Q stands for quantity. Q is equal to x times y squared, where x and y are positive numbers, in other words, greater than 0, where x plus y squared is equal to 1. Okay, so the goal is to take whatever this value is, think of this as our output, and we want to find the maximum value that this could take on if Q is equal to x times y squared, where x and y, we're thinking of those as the inputs that contribute to this total quantity. Now, in addition to a definition for the quantity, we also have specific limitations on what x and y can be, what those input values can be. So we know the input values both have to be positive numbers, so they're both going to be greater than 0. So let's make a note of that. So both x and y have to be greater than 0, based on the fact that we've been told that they will be positive numbers. And then we've also been told that x and y are related in a specific way. This is the relationship between x and y. So x and y are input components that contribute to this quantity, this total that we're attempting to maximize, but the input resources are subject to this limitation. They have to be values that satisfy this equation. So this particular piece of information is also going to be important in addition to knowing that x and y have to be positive numbers. Now, as soon as I see the term maximize or potentially the term minimize, I know we're going to use one of our calculus techniques. We know that maximum and minimum values occur wherever we have a critical value with one of our functions or something related to a critical value. We find the critical values for our function, or in this case our quantity, by taking the derivative, setting the derivative equal to 0, and then solving for our variable. Now, the only issue here, as it currently stands, is we have an output variable, but notice we have two input variables in this case. So if we were to just attempt to take the derivative right now, are we taking the derivative with respect to x, with respect to y, with respect to both? We can't really do that as this equation currently stands. We have to get our equation in terms of one variable. So essentially what this is going to look like is a system of equations. It's going to be essentially a system of equations, and then we're just going to add in a little bit of calculus to our solution technique. So one technique you use to solve a system of equations is substitution. If you have two equations that are relating your variables, then if you can take one of them, in this case the one that gives the limitation on our inputs, and isolate one of the variables, you can then substitute for that variable into your other equation, which will give you a new equation where one variable has been eliminated, and now we're just in terms of the variable we're going to focus on. That, in this case, means we want to either substitute in place of x or substitute in place of y to take this equation with three variables and just have it in terms of q, and then either x or y, but not both. So over here, again, we're going to isolate one of these variables, substitute for it, and then simplify this equation. So which variable are we going to isolate? Well, it ultimately doesn't matter which one you choose. Choose which one is going to be easier to isolate. So in this case, x will probably be easier to isolate, because if we want to isolate y, we have to take a square root, which is potentially problematic. So we can isolate x just by subtracting the y squared from both sides. So x is equal to 1 minus y squared. So because our problem is defined by both of these equations at the same time, we know that this equation has to be true regardless of what else is going on in the situation. What that also means is that wherever I see an x anywhere in this problem, I could put a 1 minus y squared and still have an equivalent expression. So I'm going to substitute in place of my x in this equation representing the value that I want to maximize. So my new equation is going to be q is equal to, and then in place of x, we're going to sub in this equivalent expression, so 1 minus y squared, and then we already had a y squared, so that's then multiplied by our parentheses. This needs to distribute in parentheses, so that's going to be y squared minus y to the fourth power. And so what we now have is a version of the expression for our quantity that only contains one variable, because again, we eliminated the variable x by performing a substitution. We can now take the derivative of our quantity, and that's going to lead us to the techniques we've talked about with respect to maximization and minimization. So I want to take the derivative of quantity, and in this case I'm taking the derivative with respect to the variable y, because my expression for q is now in terms of y. So what I would normally do in terms of x, I'm going to do the same thing, but I now just have a variable y. So I can use the power rule for each of these terms. So for the first term, I'll bring down my 2, decrease the exponent to 1, and then for the second term, bring down the 4, and then decrease the exponent to 3. Okay, so this is the value of our derivative. We want to find potential values for y where this would be maximized, and we know those values are always going to occur wherever we have a critical value. Critical values are going to occur where our derivative takes on a value of 0. So I want to know what values of y would lead the expression for my derivative to be equal to 0. Okay, so we've solved equations like this quite a bit at this point. Again, don't move a term over to the right and divide out the variable. You can't do that. You're going to have to factor. It doesn't matter that it's y instead of x. You factor it the same way you normally would. So look for a greatest common factor first. So notice both terms have a 2 in common, and they also have a y in common. So we're going to factor out a 2y, and that's going to leave me with 1 minus 2y squared, and that's equal to 0. I can now split up my factors and set each of them equal to 0. And then I now have two smaller equations where I can solve for y. So in my first equation, I'm just going to divide out 2 from both sides. So that leads me to the value y is equal to 0. And we'll come back to this. Let's solve this equation as well. Now here, I only have one instance of the variable, unlike this original equation. So anytime I only see one instance of the variable, I can isolate it. I can move terms around and just isolate my variable. So I can subtract 1, or I could think of just adding the 2y squared to both sides. It's not going to make a difference which way we go. So I'm going to add it to both sides, so that gives me 2y squared is equal to 1. So y squared is equal to 1/2, 1 divided by 2. And then I need to take the square root of both sides. Now, when we take the square root in an equation, we put a plus or minus on the side containing our constant. And so this corresponds to 2 solutions given the fact that we had an original equation that had an exponent of 2. So what we're saying now is that there are 3 potential values where we might hit a maximum for this particular quantity in question. Now let's go back to the problem description because there was a little bit more information that may be helpful in this case. Notice we had the restriction that x and y had to be greater than 0, strictly greater than 0, which is the definition for a number being positive. Well, that means y is equal to 0 is not a possibility based on the problem description. So y equals 0 is not a value that we have to consider. Now also, the square root of 1/2, we know that's going to be a positive number. So the positive version of that, well, that's a positive number. But the negative version of that is negative. So based on that restriction, we only want to keep the positive square root of 1/2. We're not going to keep the negative version because, again, it violates the restrictions in the original problem. So in that case, only one of the critical values actually applies in this situation. So in theory, that should be the value that maximizes this quantity. However, we do need to verify that this does in fact represent the location of a maximum. We don't necessarily know that until we verify that. So I'm going to set up my little table, and then I'm going to put my critical value on my table. The critical value is the square root of 1/2. And then we want to check the sign of the derivative on either side of this location. So at that particular value of y, we know the derivative has a value of 0. We want to know what happens for values that are less than the square root of 1/2 and values that are greater than the square root of 1/2. What sign does the derivative take on? So we can actually graph this one if we want. So I'm going to graph 2y minus 4y cubed. So 2y, oops, let's go into the graphing utility. Now we're doing it in terms of y here, but keep in mind, think of this as just the output and then whatever we have as an input. So we're going to type x, but in the actual problem we're thinking of y as the input. So 2 times our variable, whatever it happens to be, minus 4 times our variable raised to the 3rd power. And let's look at the graph. Let me go back to Zoom Standard. And there we go. There's our graph. Okay, so how can we identify what we're looking at? Let me zoom in just a little bit more. Stay centered at the origin. Okay, so now we can see all of those locations where we had a critical value. Remember, a critical value is a location where either the derivative is undefined or where the derivative takes on a value of 0. So in this case, we see the locations where our derivative takes on a value of 0 by noticing where those x-intercepts are. So we have an x-intercept at 0, there at the origin, and then we also have a negative x-intercept to the left of that, and then a positive x-intercept to the right of that. Those we will find will be at the location square root of 1/2 and negative square root of 1/2. Now the central intercept there at the origin and the one to its left, we already know we're not going to consider those for purposes of this problem because again they violate the restrictions we have at the very beginning that all of our values have to be greater than 0. So all we're interested in is that positive intercept there at the square root of 1/2. Now since we're looking at the value of the derivative, we're asking the question, what's happening on either side of square root of 1/2 if we look at that intercept? Well, if you look to the left of that intercept, right before you cross over, notice we're above the x-axis. So the value of the expression is going to be a positive number. So for values greater, or excuse me, less than root 1/2, we know we have a derivative that is going to be positive. That means that our function is going to be increasing over that particular region. And again, we have other critical values over here. We're not worried about those. Now to the right-hand side, when we're looking at values that are greater than our critical value, notice the derivative drops so that it's below the x-axis, so it takes on a negative value. If our derivative is negative, that means our function is decreasing. So the graph would be shaped like that at that particular location. So we go from increasing to our critical value and then decreasing from there, which means we do have a maximum represented at that particular critical value. And the goal for this problem was to maximize our quantity. So what this tells us is that the maximum value for our quantity is going to occur where y is equal to the square root of 1/2. Now, we're not quite done yet. Notice we have two input variables, both x and y, and they're related in this particular way. So we've determined the value of y that's going to maximize the quantity, q. We also need to know what the associated value of x would be. So x is defined as 1 minus y squared, and we know our y here in this case is going to be the square root of 1/2. So that's going to be 1 minus the square root of 1/2 squared. Well, we square a square root, and it just rationalizes. So 1 minus 1/2, and that's going to give me a value of 1/2. So that is going to be the associated value of x. Well, then the final question is, what is the maximum value for this quantity? We want to maximize the quantity, and we know the maximum value for the quantity is going to occur when this is our y value, and then this is the x value that goes with it. So the actual value for our quantity, q, we know q is equal to x times y squared. We know the maximum occurs when x is 1/2 and y is the square root of 1/2. So 1/2 times the square root of 1/2 quantity squared. Again, we're squaring that square root, so that's going to rationalize it. So we have 1/2 times 1/2. We multiply straight across numerator and denominator, and that's going to give us 1/4. So 1/4 is going to be the maximum value of that function q, and we know it occurs specifically when our input variable x has a value of 1/2 and our input variable of y has the value of square root of 1/2. Now, it's worth noting that when we did the substitution, we solved for x and then substituted and eliminated x. We could have done the same thing by solving for y. The only reason we didn't solve for y, again, is because we would have to take a square root, which means you have to deal with the plus or minus issue, which ideally we'd like to avoid. But theoretically speaking, we would get to the same answers if we were to have isolated y first and then substituted in place of y. The problem would have worked out the same way. So let's try another one similar to this. We've got a quantity, we either want to maximize it or minimize it, and we have some specific limitations on the quantity. Okay, so we want to minimize q is equal to 2x squared plus 3y squared, specifically subject to the constraint x plus y is equal to 5. So here we don't have any limitations on x and y being positive numbers. All we know is that whatever x and y are that contribute to this total, they have to specifically add up to a total of 5. So we want to minimize this quantity this time. Now, similarly as before, we have a quantity that we want to minimize. We know we're going to have to take the derivative, but as of right now, we still have two variables, so we're not in a good position to be able to differentiate because we're not sure which variable we're going to differentiate with respect to. So we're going to use the same strategy as before. We're going to take the constraint, the limitation on our inputs, and we're going to use it to substitute for one of the two original variables, thereby putting us in a better position to be able to differentiate from there. So since we substituted for x last time, let's substitute for y this time. So I'm going to isolate my y. So y is equal to 5 minus x, move that over. So that tells me wherever I see a y in this problem, I could put a 5 minus x instead because they are equivalent. So in place of my y in this problem, I'm going to sub in that expression, 5 minus x. So 2x squared plus 3 times the quantity 5 minus x squared. Now we have an equation entirely in terms of this single input variable. Ideally, we want to clean it up a little bit before we take the derivative though. So what does that look like here? Well, we need to FOIL out 5 minus x squared, and then we'll have to distribute 3 once we FOIL it out. So FOIL it out first and then distribute the 3. So if we FOIL this out, that's going to be 25 minus 10x plus x squared. Okay, and you can go pause the video, double check that if you need to. Definitely worth doing. Make sure you get down to that. Okay, distribute the 3 to all three terms. So that's going to be 2x squared plus 3 times 25 is 75. 3 times negative 10 is negative 30, so negative 30x. And then 3 times x squared plus 3x squared. Now notice we now have two like terms, so let's combine those together. And typically we write our terms highest exponent to lowest. So 2x squared and another 3x squared is going to give us 5x squared minus 30x plus 75. So this is now our expression representing the quantity in terms of this variable x. So this is what we want to maximize. We know the maximum value of this quantity is going to occur, again, wherever we have a critical value. So we're going to differentiate, determine what values of the input variable result in the whole expression being equal to 0. That's going to give us our critical values, and then we'll go from there. So the derivative of our function, now we're doing it with respect to x, since that's the variable we have left. And again, we can just use the power rule here. So that's going to be 10x minus 30. Okay, so what makes our derivative 0? Where do we have a critical value? So I'm going to take my derivative, set it equal to 0. Now here this is just linear, so I can just isolate my x. Move the 30 over. So 10x is equal to 30. Divide by 10. So x is equal to 3. Okay. Now, does this in fact represent the location of a minimum value? Because the goal was to minimize this expression. Well, again, same kind of strategy as before. We need to determine what happens on either side of that critical value when we look at the derivative. So they're at x equals 3. We know that's where our derivative is equal to 0. Well, what happens to the left of that? What happens to the right of that? Does that behavior confirm that we do have a minimum at that location? So let's go and let's type in this derivative. So this derivative is going to be 10 times x minus 30, and let's graph it. Let me zoom back to zoom standard, and we expect to see an intercept at x equals 3, and sure enough, we do. So what's happening to the left of that intercept? What's happening to the right of that intercept? Well, to the left of the intercept, our graph for our derivative is below the x-axis, which means the derivative has a negative value. Well, anywhere where the derivative has a negative value, our actual function is decreasing. So we know to the left of this critical value, our function is decreasing. Now, once we cross over that intercept, we go from being below the x-axis to being above, where the derivative is positive. If the derivative is positive, then we are increasing. So we go from decreasing to increasing, which means that our critical value does, in fact, occur at a minimum. It represents the location of a minimum. Well, that confirms what we need to know. So now we just need to know what's the value of the other input, and then what's the associated minimum value for our function based on the values we end up with for our inputs. So we know that our other input, y, is defined as 5 minus x, based on how they were originally related to one another. So subbing in the value of x that we just found, which was 3, 5 minus 3 is going to be 2. So the value that y needs to take on in order to minimize our quantity is going to be the value 2. So the actual quantity is equal to 2 times x squared plus 3 times y squared. We want to minimize this, and we know the minimum value of this quantity is going to occur when x is equal to 3 and then y is equal to 2. So let's sub those in. So 2 times x, which is 3 squared, plus 3 times y, which is 2 squared. Okay, simplify your exponents first. So 3 squared is going to be 9. 2 times 9 is going to be 18. And then 2 squared is 4. 4 times 3 is going to be 12. So 18 plus 12, which is equal to 30. So 30 is going to be the minimum value that this quantity takes on, and that minimum value occurs when we have an input of x equals 3 and an input of y equals 2. So both of these problems have been out of context, just minimizing some abstract quantity, maximizing some abstract quantity based on specific information about how the inputs to the quantity are related. So the general idea, again, is if we have more than one input, use the information that relates our inputs to isolate and substitute for one of them, which is then going to generate a version of your function that only has the output variable and then a single input variable. Once we have that single input variable, we can take the derivative, and we know we take the derivative because that allows us to identify locations for maximum and minimum values, which is our ultimate goal. So we perform that differentiation, find our critical values, determine where we have a maximum or a minimum using the value of the derivative. Remember, if the derivative is negative, that means our function is decreasing at a particular location. If the derivative is positive, our function is increasing at that location, and then we just go from there. So once we confirm that we have a location for a minimum or a maximum, essentially it's just reverse substitution. Find the other input value, and once you have your two input values, you can determine the associated value for whatever quantity you're interested in. So let's now take these strategies that we've looked at and let's solve some actual application problems, actual context. Now, because these are what we can think of as word problems, if you want to think of them that way, being very careful, reading carefully, reading the problem a couple times is always going to be a good idea, particularly if it's describing some type of physical situation. It's a good idea to be able to draw a picture if you can. That sometimes takes a little bit of work. It's not always obvious what the picture may look like, so taking your time and really breaking down the problem is going to be very important. So if there is an associated picture that you can draw, you want to do that. And then you also want to make a list of everything you know and what you're trying to determine. So what have you been given in the problem, and what is the problem asking you to do? Those kind of things are going to be important to do up front. Don't just dive in and try to find a derivative. In a lot of situations, you're going to have to actually write the expression representing your quantity, what you're maximizing, what you're minimizing, and determine how it's related to your input variables, whatever that may be. So take your time, draw a picture, write down everything you can, make a list of all the information you know, what you don't know, what you're trying to find, and then you go from there. Okay, so let's go through the example. So a hobby store has 20 feet of fencing to fence off a rectangular area for an electric train in a corner of its display room. So the two sides up against the wall aren't going to require a fence. We want to know what dimensions for the rectangle are going to maximize the area that we can create, and what's the maximum area going to be. Okay, so we've essentially picked a corner of the room. We want to fence off the corner of the room. We don't have to have fencing along the walls, but we need to have fencing enclosing it, and we want to enclose it in the shape of a rectangle. Now, we're limited as to how much fencing we can use. We only have 20 feet to use. So the idea is we want to optimize how we use this fencing so that we can fence off the largest possible area. So let's draw a picture of this. Well, we know we're doing a rectangle, so let's assume that those are the actual fence lengths we want to use, and so the walls are going to be over here. Now I'm going to draw the walls as dotted lines because we know we don't actually need to use any fencing up against the walls. So the solid lines represent locations where we're actually splitting up and using our 20 feet of fencing. And the dotted lines, those are the walls, those are the areas where we don't actually need anything. So we want to maximize the area. We want to know what dimensions will maximize the area that we fence off, and what is the maximum area that results. Well, area is going to be the quantity. Think of that as our output quantity. That's like Q in this situation. So what are the inputs going to be? Well, based on what we're doing, we're determining what is the length of our fencing that we're going to use and what is the width that we're going to use. So that's a general idea of sort of what we're looking at visually speaking. Now keep in mind we only have to use the width once. We only need to use the length once as well, because again these other two sides are not actually being fenced in. So let's make a list of what we know and what we're solving for. So what are we solving for? What's the goal? We want to maximize the quantity A, which represents area. Represents the area of the rectangle that we fence off. Now what do we need to do in order to do that? Well, we need to find the associated length and width. So we want to find the maximum value for area, and we also want to find the dimensions that are going to maximize it. So we have 3 unknowns. We need to find all of those by the end of the problem. And what we've been given is that there are 20 feet of fencing to use. So 20 feet of fencing. Now, it makes sense that in order to maximize the area we can create, we need to use all of it. So using less than the whole 20 feet is going to leave us with an area that's smaller than what we could ultimately accomplish. So we are going to have to use the whole 20 feet that is going to be given. So here's where we need to actually write the equation, determine what the relationships are in this problem. Because we don't really have a function at this point. We have a quantity that we want to maximize. We know what our input variables are, but how are all of these things related? Well, in this case, we're looking at a geometry problem. So area and then length and width are going to be related via a geometric formula. So the next thing we want to do is we want to write any relationships we need that relate all of these quantities. So first off, let's focus on A, the quantity we want to maximize. What do we know about A? How is it related to our input variables? Well, if we're talking about a rectangle, area is always defined as length times width for a rectangle. Now you may be asking the question, does it make a difference that we're not actually using fencing here? The answer is no. Area is the space inside. So whether we actually have fence on all four sides, or two sides, or just one side, that's not going to make a difference in how we define the area. The area is only dependent on the shape that we draw. So in this case, the area is going to be our length times our width. Now, how are length and width constrained? Well, we're using this length one time, we're using this width one time, and we know we have 20 feet in order to draw the width and the length. So we also know that when we use the length, when we determine what that's going to be, and when we add up the width that we're going to use, in other words, the lengths of both sides, that has to add up to be exactly 20 feet, so that we use all of our resources. So these are going to be the relationships we use to maximize the situation, to maximize our area. So this is the quantity we're maximizing. This is the restriction on our variables L and W. So now it's basically the same kind of problem we just did. So we want to maximize this value, which means we're going to take its derivative, but again, we still have two variables, so how do we differentiate? We can't do that yet. So we're going to take our restriction equation, isolate one of the variables, it doesn't matter which one. Let's just say we want to isolate L. So we have L is equal to 20 minus W, and that can then be substituted in for our variable. So we're going to take our quantity equation, so area is equal to length times width. We're substituting for length. So we've defined length as 20 minus W based on our constraint. And then that's also multiplied by W based on our area formula. Now distribute the W into parentheses. So we have 20W minus W squared. So this is now the expression for our area, completely in terms of the variable W and not the variable L. So now we can take the derivative, which will allow us to find where we maximize, where we minimize, depending on the situation we're in. So we're taking the derivative of area with respect to the variable W, which is our existing variable now. So differentiate one term at a time, so that's going to be 20 minus 2W. Okay, we know our maximum and minimum values always occur where we have those critical values. So what's going to make this derivative 0? So we'll set it equal to 0. So 20 minus 2W is equal to 0. I can add 2W and move it over. So we have 2W is equal to 20. Divide by 2. And W is equal to 10. Well, 10 what? What is the unit in this case? We need units in an applied situation. 10 feet. We're talking about feet of fencing. This is going to be the width that we use. Now, how do we verify that we are in fact talking about the location of a maximum for our quantity in question? Again, that's when we're going to go and we're going to analyze what's happening with the derivative around that value. So there, around that critical value where W is equal to 10, what's happening on either side of that location? Well, let's see. So I'm going to type in my derivative, 20 minus 2W, or 2x. The variable is arbitrary. And then there's our graph for that. So let me zoom out. Okay, we have an intercept at 10. We can see that intercept at 10. What's happening to the left of that location? What's happening to the right of it? Well, to the left of that location, the graph of the derivative is above the x-axis, which means the derivative is positive. Anywhere the derivative is positive, our function is increasing. And then once we go past that intercept at 10, we flip down below the x-axis, our derivative is negative, so our function is decreasing. So we go from increasing to decreasing, which means this represents the location of our maximum. So based on that, we then can find our other values. So length is defined as 20 minus width. which is going to be 20 minus 10, which is equal to 10. And again, 10 what? 10 feet. So our area is maximized when width is 10 feet and length is also 10 feet, which means we haven't truly drawn a rectangle, we've drawn a square when we fenced off this area. So what is the resulting area going to be? Area is length times width. So length is going to be 10 feet. Width is going to be 10 feet. And so our area, the maximum area we can create with this 20 feet of fencing is going to be 100. And then in this case, it is feet squared, square feet. In general, a square always maximizes your area. In absence of any other situation, a square is going to maximize the area that you can draw. So there we go. Really no different than the previous two problems, except we had to do this part ourselves. Previously, we were given this information. We have to interpret what the problem is telling us in order to determine that information ourselves. But past that, every single problem like this is pretty much routine. Okay, so let's try another one. Let's try a similar one, but let's take it up a notch. Okay, so a food company is constructing an open-top, square-based, in other words, the base is a square, rectangular metal tank that is supposed to have a volume of 32 feet cubed. Volume means length times width times height. Okay, so we're talking about the physical space that we take up from a three-dimensional standpoint. So we want to know what dimensions for this container will minimize the surface area. In other words, if we take the area of all the sides, what's going to minimize the amount of area, and then what is the minimum surface area. So the idea here is we want to have a container that can hold a volume of 32 feet cubed of whatever it happens to be holding, but by minimizing the surface area, we're minimizing how much metal we have to use to create something like this. So minimizing the surface area means we're minimizing the resources we have to use to create a tank that looks like this and has this particular capacity. So let's draw a picture. So it's a rectangular prism, if you just want to call it that. That's formally speaking what it is. It's a rectangular prism, but the top is going to be open. Now we know that the base is a square, and we can indicate that based on how we label the diagram once we have the diagram. So the front of the tank is a rectangle, okay, and then I'll draw a diagonal like that. It takes us back, and then we draw a diagonal right there, and there's our tank. Now, in order to show you that it is truly three-dimensional, and so we have a sense of what we're really looking at, here's a way to do that. So the top is open, so you'd be able to see the back edge through the top. But because the rest of it is metal and it's solid, you wouldn't be able to see the edge once you get inside the tank. So we can use dotted lines to show that. Now, don't worry if it's not intuitive how to draw something like that. That's okay. If you can just draw a cube and you can label a cube, then that's all you need to be able to do. Okay, so let's label this. Let's assign some variables. You can use length, width, height. You can use X and Y. Ultimately, it doesn't matter. So what do we know? Well, we know the base of this tank is going to be a square, which means our length and our width are going to be the same. So I'm just going to label them with one variable. I'll just use the variable L because length and width, they're going to be the same. And then our third variable for volume is going to be height. So we only have two variables even though we're talking about 3 dimensions because we know the base is a square. Okay, so what are we solving for? What are we given? All of that good stuff. So the goal, the ultimate goal is to minimize surface area. To take something that looks like this and minimize how much metal we have to use to create that. So I'm going to call surface area capital S, S for surface area. Okay, so we want to minimize the surface area. How many sides do we have? Well, we have 4 vertical sides. We have the base, and then the top is open. So we have 5 sides in total. That's going to be important to keep in mind. So what do we want to do then? In order to minimize it, we need to find the length and the height that's going to be associated with that minimum surface area. And we've been told that the volume we need to create is 32 feet cubed. Now it's in terms of cubic feet because we're looking at 3 dimensions. So 1, 2, 3 dimensions, volume is feet cubed. So now we need to relate everything. We need an expression for the quantity that we're minimizing in terms of our variables. And then we need an expression that's also going to take the information we were given about volume and also relate it to the input variables so that we have that constraint on those variables. So let's start with the surface area. So we're going to go step by step. We want to go one side at a time. So we determine there's going to be 5 sides. So the total surface area for something that's constructed like this is going to be what it would take to take the area of each side and add all of those sides up. So 5 sides in total. So let's start with the base. The base we know is filled in. So it's length times length. So length squared would give us the surface area of the base. So that's going to be one side, length squared. Now what about the front of it? Well, the base is just L, and then this particular value is going to be H. So notice H is labeled over here, but all of these vertical edges all have a length of H because we're talking about a rectangle, so all of those are going to have the same height. So H, 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 they all have a value of H. So the front of the container is going to be length times height. So plus length times height. Now what if we were to look at the next one? Well, that's also length times height, and then length times height, and then length times height. So all of the vertical sides all have the same area. So we could add up LH, 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 LH 4 times, or just take that one time and multiply it by 4. And that's going to represent all of the vertical sides of the container. So length squared, I'll label everything, that's going to be for the base. And then 4LH is going to be for the vertical sides. Okay, but assuming this was all we knew, we could minimize surface area by just making this as small as we want. The smallest L can go, the smallest H can go is going to minimize this value. But that's not the whole story, because we know that we also have to create something that has a volume of 32 feet cubed. Well, what is volume going to be? Volume, if we're talking about something rectangular, a rectangular prism, is all 3 dimensions multiplied together. So if you were to multiply and get the area of the base and then multiply that by the height, that's going to give you the volume, the amount of stuff, for lack of a better way to put it, contained inside this particular container. So volume is equal to L times H. So L squared times H. Now we haven't created a new variable here. We don't actually need this because what do we know? If this is the expression for volume, volume is supposed to be equal to 32 feet cubed. So that is equal to 32. So now we're in the same kind of situation that we've been in before. We have the quantity that in this case we want to minimize. It's in terms of our 2 input variables. And then we have the relationship between the variables that's going to tell us how one limits the other. So I need to isolate one of these variables so that I can sub it in over here and then give myself something that only has 2 variables so that I can take my derivative. Now the easiest variable to isolate here is going to be the H, because if we want to isolate L, we've got to take a square root, and let's try to avoid that. So based on this relationship, h is going to be 32 divided by L squared. So there's our expression for h. That can now be substituted into that expression for our quantity for surface area. So S is equal to length squared plus 4 times length times h, and that's when we substitute. So h is 32 divided by length squared. So let's simplify that down. This term, we now have length in the numerator. You can think of this as being over 1 if you need. So there's 1 L in the numerator, there's 2 in the denominator. Those can cancel out and we're just left with 1 in the denominator. So that's going to be L squared plus 4 times 32. Let's multiply that. So 4 times 32 is equal to 128. So plus 128. And then we're left with 1 L in the denominator when we reduce those common factors. So 128 over L. Okay. So what do we need to do now? We need to take the derivative. So the derivative of S with respect to L, okay, what's that going to be? So when we take our derivative, bring down the 2, so that's going to be 2L. Now here, maybe write this as 128 times L to the negative 1. We've used that strategy before, so we can use the power rule so that we can bring down the exponent. So that'll be minus 128, and then decrease the exponent by 1, so that would be L to the negative 2. Okay, we know that negative 2 means flip it, take it to the denominator. So that's going to be 2L minus 128 over L squared. Okay, so now that we have that, we need to know what makes that equal to 0 or potentially undefined, depending on the situation we're looking in. So let's take that and let's set it equal to 0. So 2L minus 128 over L squared is equal to 0. Now I am going to move this term over this time. I'm not dividing anything out. I'll show you what I'm going to do in just a moment. So 2L, move the other term over, so 128 over L squared. Now that I have that on one side, I can then multiply by the denominator, move that over, and then we'll be in a better position from where we currently are. So I'm going to take it back up here. So if I multiply both sides by L squared, that's going to give me 2L cubed. So L times L squared, move it over, it's going to be L cubed, is equal to 128. Okay, now we only have one instance of the variable, which means we don't have to factor, we can just isolate it. So divide out 2. So L cubed is equal to 128 divided by 2, which is going to be 64. Now we're taking a cube root. So L is equal to the cube root of 64. Now a cube root is not like a square root. You don't need the plus minus. That only applies when we're looking at a root that's even. The cube root, there's only one value for it. It's not a plus or minus kind of situation. Now if you've never done a cube root on a calculator, your calculator can do it. So right above x squared we have the square root. The cube root is under the math menu. So if you were to go to the math menu, notice option 4, there's a little 3 in front of the radical, that's a cube root. Now just for the sake of mentioning it, right below it, that's X in the window, which means you can type in any type of root you want. So if you wanted a 4th root, a 5th root, that would be the button you'd use there. So we want a cube root, and we want the cube root of 64. And that is going to be 4. So that's going to be the length we want, supposedly. We do need to verify, though, that this does represent the location of a minimum for our quantity. So let's go back, let's look at the derivative around that value at 4. Okay, I'm going to type in the expression for my derivative. So where is that? That's down here, that's that expression. So 2L, we'll just call it 2X minus 128 divided by X squared. Okay, so your calculator knows, do the division, treat that as one term, and then it's 2X minus all of that. So let's graph that. And then go back to a zoom standard. Okay, there we go, and there's that intercept at 4. So what's happening to the left of that? What's happening to the right? To the left of that, the derivative is below the x-axis, which means the derivative is negative, which means our function is decreasing. And then to the right, we're above the x-axis, the derivative is positive, so our function is increasing. So this does represent the location for a minimum. So when L is equal to 4, that is going to be the value that minimizes our surface area. What is W going to be? Or not W, H, excuse me. H is defined as 32 divided by L squared. So 32 divided by L squared, which is equal to 32 divided by 4 squared. 4 squared is 16. So 32 divided by 16, which is equal to 2. So 2 what? Well, we're talking about feet. So 2 feet and 4 feet. So these are going to be the values of our input variables that are going to result in the smallest amount of surface area. So what is that surface area going to be? Let's go back to the expression for that. So L squared plus 4 times L times H. So L squared, so 4 squared plus 4 times L, which is 4, times H, which is 2. So 4 squared is going to give us 16. And then 4 times 4, 16. 16 times 2 is 32, so plus 32. Add those up, and that gives 48. 48 what? Let's be careful here. We're not talking about volume. Although we're in 3 dimensions, we're talking about area. We're talking about taking the area of each of the sides, adding all of that area up, and that's the surface area. So because it's area, it's going to be in feet squared. So 48 feet squared is going to be the minimum area that we can get for a container of this size so that it can contain 32 cubic feet of volume. So there's a couple of examples of geometric, physical situations where we can draw a picture representing the situation, use what we know about the values, the quantities, how they're related to one another, specifically the quantity that we either want to maximize or minimize, and then the input variables. And then we go from there and use the same strategy. Take your constraint, use your constraint to change your expression for the quantity to put it in terms of one variable. And then we take our derivative. We find the critical value or values for our derivative, determine where we maximize or minimize, verify that, of course, using the derivative on either side of the critical value, and then it kind of just takes care of itself from there. So let's try one more situation, not a physical situation where we can draw a picture, but still an important kind of applied situation. Okay, so now we're going to talk about a financial situation, specifically looking at cost, revenue, profit, how we can find an optimal situation when we're talking about these kind of quantities based on how one is related to the other. Okay, so a car audio company determines that in order to sell X units of a new stereo, the price per unit in dollars must be defined by P of X is equal to 1,000 minus X. So this is what we call a pricing function. So based on the number of units you want to sell, that'll be the variable X. You sub in that value, and this is going to assign the price that you'll want to charge in order to have that many items sell. So the fewer items we sell, the higher the price is going to be. The more items we sell, the lower the price has to be because we're selling more. Now, we've also been told a little bit of information about this company's costs. So the variable cost of production per stereo is $20. In other words, that's the amount of cost for resources, for all of the raw materials that go into production, for the labor that goes into production. So per stereo, it costs $20 to make. So one stereo costs 20, two stereos cost 40, and three cost 60, so on and so forth. Now the company also has fixed costs of $3,000 for production. So what does that mean? Well, those are costs that the company is going to incur whether it makes anything or not. So if it makes 1,000 stereos, fixed costs are $3,000. If it makes 0 stereos, fixed costs are $3,000. That's like paying for your utilities, paying taxes, those kinds of things. Things you have to pay regardless of how productive or not productive your company is. So we want to write functions representing cost and then revenue and then profit, which is related to cost and revenue. And then we want to maximize profit, determine how much we'd have to make and sell in order to maximize our overall bottom line, our profit. So first thing we want to do, find a linear total cost function. So the general structure of a cost function, when we're told that it is intended to be linear, it's going to be based on our two costs. So the cost per stereo is $20 to produce one stereo, and then the company has $3,000 in fixed costs. So the $3,000 we pay no matter what. So the formula for cost is going to be fixed cost plus variable cost times X, where X is the number of items that you make, the number of units that you make. So the amount per unit times the number of units you make plus the extra cost you have to pay even if you make nothing. So keep in mind, if X were 0, if you look at a formula like this, if X were 0, you'd sub in 0 here, which would eliminate this term, but that still means your costs are equal to the fixed cost. It still means you have to pay the $3,000 even if you don't make and sell anything. So in this case, our fixed cost is $3,000, so that's going to be $3,000 plus our variable cost, which is 20, times the number of units, which is X. So that is going to be the function representing our cost. Again, X is the number of stereos that we produce. We also want to find the total revenue function. Revenue, that's the money we put in the cash register. It's not the bottom line. It's before we pay our bills. So revenue is always defined as price times X. Now, depending on the situation, price may be a given flat amount that may already be determined. In this case, we have a pricing function which tells us that the price will vary depending on what the value of X is. So in place of just a flat price, we're going to sub in the expression for the price function. So the price function, the expression for determining price, is going to be 1,000 minus X, and of course that's in dollars, or whatever your currency is, times X. So just to clean this up, we can distribute the X into parentheses. So that's going to be 1,000 X minus X squared. And so where X is the number of units we sell, we plug this in, and whatever this is in dollars, that's going to be the amount of money that goes into the cash register. And again, that's before you pay your bills. So what happens when you pay your bills? Well, you take the money you've made minus your costs, paying your bills, and the difference between the two is your profit function. So profit is defined as revenue minus cost. And so in this case, we're going to take our revenue function minus our cost function, and that's going to give us the expression for the profit function. So R of X is defined as 1,000X minus X squared. And then C of X is going to be 3,000 plus 20X. So cleaning all of this up, the one thing to be careful about is notice everything in parentheses over here has been subtracted. That subtraction has to distribute to both terms. So So if we want to list highest exponent to lowest, we have a negative x squared, that's the only quadratic term, so negative x squared, and then we have 1000x minus 20x, which leaves us with positive 980x. And then we're also subtracting 3000. And that is our profit function. So the underlying assumption here is that everything we make, we also sell. So X is defined as the number of units. Well, here it's the number of units we make. Here it's the number of units we sell. If we're talking about profit, profit includes both what we've sold and what we've made. So you can think of it as sort of a make-to-order business. You're not going to have any surplus, nothing's left over. Everything you make, you sell. So the profit is the difference between what you've made and what it took to make it. Okay, so then the question is, now we want to know how many units, in other words, X, what is X? How many units must be made and sold in order to maximize this profit? And what is the associated maximum profit? Well, we don't have any additional constraints on our variables, and notice also what we want to maximize. The quantity we want to maximize is P for profit, and already the expression for P only contains one variable. So all of the constraints on the inputs have already been determined based on how we set up these functions. So the constraints were based on the original problem description and all of the values given in that problem description. So we already have a function that we can differentiate in its current form. So we want the derivative of profit with respect to the variable x, where the x is the number of units made and sold. So take the derivative, bring down our 2, so negative 2x, and then differentiate here, plus 980. Okay, so what is our critical value? So negative 2x plus 980 is equal to 0. Let's add the 2x and move it over. So 2x is equal to 980. So x is equal to 980 divided by 2, which is going to be 490. 490 what? 490 stereos, since we're making stereos. Well, how can we be sure that this represents a maximum? Well, let's look at that critical value and let's look at the derivative on either side of that location. So 490 is our proposed location for maximization. And let's plug in the derivative. So negative 2x plus 980. And we can't see it, that's because our numbers are big, so let's zoom out. Still can't see it. Let's zoom out a little bit more. Still can't see it. Okay, so that's a good indication that maybe we want to use the table. Remember, we can use the table to get the same information. So let's go into our table. Okay, now it's already set up with given x values. We need to get all the way to x equals 490 and plus. So I'm going to change my table settings so that I don't have to scroll. Remember, we can change the independent variable to ask, and we can just type in whatever x values we want. So I'm going to set that, and then I'm going to go back into the table. So we want to know what's happening for values that are less than our critical value and values that are greater than our critical value. It doesn't matter how much lower or how much higher, that's our only critical value. So anything that happens to the left happens for every value to the left. Anything that happens to the right happens for every value. So even just 1 unit less, 489. If we're looking at 489, the value of the derivative is 2. Most importantly, it's positive. So because the derivative has a positive value, we know our function would be increasing for values less than the critical value. What about 1 unit greater, so 491? Well, now we change over to having a negative derivative, which means our function is decreasing there. So we go from increasing to decreasing, which means 490 does represent the location of our maximum for profit. So 490 stereos made and sold will maximize our profit. What is the profit going to be? Well, it's going to be P of 490. So plug it into our profit function, which is going to give us the actual dollar amount. So negative 490, careful there. Notice negative is applied to the whole term. We square it before we make it negative, so be careful there. Plus 980 times 490 minus 3,000. And let's just type all of that in. We know the unit is dollars, or whatever currency you're talking about. So negative, in parentheses, 490 quantity squared, plus 980 times 490 minus 3,000. And double check it. Make sure you typed exactly what you intended to type. And there we go. That looks good. Okay, so in dollars, $237,100. That will be our profit for producing and selling 490 units. So the last question is, okay, we know how many we need to make and we know what we should make off of that. What price are we going to charge based on our pricing model? Because remember, price was not given at the very beginning. We had an expression that determines price in terms of how many items we make and sell. It's not just one flat price predetermined. So we also want to know lowercase p of 490. What is the price if we want to sell 490 stereos, which we know is going to be the optimal level of sales in order to maximize our profit? So our price function was defined as 1,000 minus x. So that's going to be 1,000 minus 490. And again, we're talking about pricing. How much are we going to charge? So that's also going to be in dollars. And it's going to be $510. So that pretty much gives us the whole picture. How much we should make and sell, how much we'll expect to make in terms of profit off of those sales, and how much we need to charge in order to meet this particular goal. So I want you to keep in mind these are 3 applications, but 3 representative of many applications. So these strategies for maximization and minimization are extremely versatile. We use them in a lot of different situations, geometric situations, non-geometric, something financial like this kind of situation. But these are really powerful strategies to be able to use. Maximization and minimization, definitely important, particularly given this idea that our resources are limited. We want to find the best outcomes given that our resources are limited. Using the derivative, using these maximization and minimization strategies, that's going to let us accomplish, it's going to help us accomplish that goal.